The zero-ohm point, also known as the reference ground, is a theoretical point where all other electrical components are referenced for their ground potential. In a grounding system, the zero-ohm point is often assumed to be the neutral conductor. However, this is not always the case. Let's consider grounding with the neutral as the zero-ohm point. In this scenario, the current path flows from the ungrounded conductor through the 10-ohm ground rod to earth, then back up through the 25-ohm neutral to the zero-ohm point. The total resistance in the loop is 35 ohms, calculated by adding the 10 ohms of the ground rod and the 25 ohms of the neutral. The current is then calculated as the voltage divided by the resistance, resulting in 3.43 amps. The 10-ohm ground rod contributes a portion of the total grounding impedance. Now let's look at grounding with Earth as the zero-ohm point. In this alternative scenario, Earth is considered the zero-ohm point. The 10-ohm ground rod and 25-ohm ground are now in parallel. The combined resistance of the parallel ground paths is 16.67 ohms, calculated as 1 divided by the sum of 1 divided by 10 and 1 divided by 25. The ungrounded conductor current is now calculated as 7.2 amps. So which scenario is correct? The choice of zero-ohm point can vary depending on the specific grounding system design. In general, it is recommended to use the neutral conductor as the zero-ohm point for residential and commercial buildings. This approach provides a stable reference point and helps minimize electrical noise. Understanding the concept of the zero-ohm point is crucial for analyzing grounding systems. By considering the different scenarios presented, it becomes clear that the resistance and current flow in a grounding system can vary depending on the location of the reference ground. This knowledge is essential for designing and maintaining safe and effective grounding systems. When analyzing grounding systems, it's crucial to understand the role of ground rods and their connection to the overall grounding impedance. A ground rod, typically made of copper or copper-clad steel, is driven into the earth to provide a direct connection to the earth. This connection serves several important functions. Firstly, it helps to stabilize the voltage to earth during normal operation. Secondly, it provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. Thirdly, it helps to minimize voltage differences between different grounded objects, reducing the risk of electric shock. The resistance of a ground rod to earth is a critical parameter. Ideally, this resistance should be as low as possible, but in practice, it can vary depending on soil conditions, moisture content, and the size and depth of the ground rod. Building codes typically specify maximum acceptable resistance for ground rods. For example, the National Electrical Code, or NEC, requires a ground rod resistance of 25 ohms or less. If the resistance exceeds 25 ohms, an additional ground rod is required. The connection between the ground rod and the grounding electrode conductor is also important. This connection must be mechanically sound and electrically conductive to ensure a reliable path for fault current. Typically, this connection is made using a listed grounding clamp or connector. The grounding electrode conductor then connects the ground rod to the main grounding busbar in the electrical panel. The main grounding busbar is the central point for all grounding connections in the electrical system. It is connected to the neutral conductor at the service entrance, creating a single point ground. This single point ground helps to minimize circulating currents and voltage differences in the grounding system. The grounding electrode system also includes other grounded objects, such as metal water pipes and building steel. These objects are bonded to the grounding system to ensure that they are at the same potential as earth. This bonding helps to prevent voltage differences that could create a shock hazard. When analyzing a grounding system, it is important to consider all of these components and their interconnection. The impedance of the grounding system is the total opposition to current flow, including the resistance of the ground rods, the impedance of the grounding electrode conductors, and the impedance of the earth itself. A low impedance grounding system is essential for providing a safe and effective path for fault current. In addition to ground rods, other types of grounding electrodes may be used, such as ground plates or underground metallic water pipes. The choice of grounding electrode depends on the specific site conditions and the requirements of the local building codes. Regardless of the type of grounding electrode used, it is important to ensure that it is properly installed and maintained. Regular inspections of the grounding system can help to identify potential problems such as corroded connections or damaged ground rods. Proper maintenance of the grounding system is essential for ensuring its continued effectiveness. In summary, a ground rod is an important component of a grounding system, providing a direct connection to earth for stabilizing voltage, facilitating overcurrent protection, and minimizing voltage differences. The resistance of the ground rod to earth should be as low as possible, and the connection between the ground rod and the grounding electrode conductor must be mechanically sound and electrically conductive. Regular inspections and maintenance of the grounding system are essential for ensuring its continued effectiveness. The concept of impedance is also crucial when discussing grounding systems. Impedance is the total opposition to current flow in an alternating current circuit. It is similar to resistance in a direct current circuit, but it also includes the effects of inductance and capacitance. In a grounding system, impedance is important because it determines the magnitude of fault current that will flow during a ground fault. A low impedance grounding system will allow a large fault current to flow, which will quickly trip the overcurrent protected device and clear the fault. A high impedance grounding system will limit the fault current, which may not be sufficient to trip the overcurrent protective device. The impedance of a grounding system is affected by several factors. Firstly, the resistance of the ground rods and other grounding electrodes. Secondly, the impedance of the grounding electrode conductors. Thirdly, the impedance of the earth itself. Fourthly, the impedance of any other components in the grounding system, such as surge protective devices. To minimize the impedance of a grounding system, it is important to use low resistance ground rods, short and direct grounding electrode conductors, and a well-connected grounding system. It is also important to avoid creating ground loops, which can increase the impedance of the grounding system. A ground loop occurs when there are multiple paths for ground current to flow, creating a circulating current that can interfere with electronic equipment. Ground loops can be avoided by using a single point ground and by isolating sensitive equipment from ground. In addition to minimizing impedance, it is also important to ensure that the grounding system is properly sized to handle the expected fault current. The size of the grounding electrode conductors and other grounding components must be adequate to carry the maximum fault current without overheating or melting. The National Electrical Code provides guidelines for sizing grounding conductors based on the size of the service entrance conductors. Surge protective devices, or SPDs, are also an important part of a grounding system. SPD protects sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. SPD work by diverting surge current to ground, preventing it from damaging the equipment. SPD should be installed at the service entrance and at any other location where sensitive equipment is located. In summary, impedance is an important concept to understand when analyzing grounding systems. A low impedance grounding system is essential for providing a safe and effective path for fault current. To minimize impedance, it is important to use low resistance ground rods, short and direct grounding electrode conductors, and a well-connected grounding system. It is also important to avoid creating ground loops and to ensure that the grounding system is properly sized to handle the expected fault current. Surge protective devices are also an important part of a grounding system, protecting sensitive electronic equipment from voltage surges. The single-point ground is a crucial concept in electrical grounding, referring to the practice of connecting all grounding conductors to a single, central point. This central point is typically located at the service entrance of a building where the electrical service enters. The purpose of a single-point ground is to minimize ground loops and voltage differences, which can cause electrical noise and create a shock hazard. In a single-point ground system, all grounding electrode conductors, equipment grounding conductors, and bonding jumpers are connected to the main grounding busbar. The main grounding busbar is then connected to the neutral conductor at the service entrance, creating a single point where all grounding paths converge. This single-point connection ensures that all grounded objects are at the same potential as Earth, minimizing the risk of electric shock. Ground loops occur when there are multiple paths for ground current to flow, creating a circulating current that can interfere with electronic equipment. Ground loops can be avoided by using a single-point ground and by isolating sensitive equipment from ground. When multiple grounding paths exist, the ground current can flow through different paths, creating voltage differences between different grounded objects. These voltage differences can cause electrical noise, which can interfere with the operation of sensitive electronic equipment. In addition to electrical noise, ground loops can also create a shock hazard. If a person comes into contact with two grounded objects that are at different potentials, they can receive an electric shock. To avoid ground loops, it is important to use a single-point ground and to ensure that all grounding conductors are properly connected. It is also important to isolate sensitive equipment from ground by using isolation transformers or other isolation devices. Isolation transformers provide a barrier between the electrical system and the equipment, preventing ground current from flowing through the equipment. In addition to minimizing ground loops, a single-point ground also helps to ensure that the grounding system is properly sized to handle the expected fault current. By connecting all grounding conductors to a single point, the grounding system is able to provide a low-impedance path for fault current to return to the source. This low-impedance path helps to quickly trip the overcurrent protective device and clear the fault. The National Electrical Code requires that all electrical systems have a single-point ground. The NEC specifies the requirements for grounding electrode conductors, equipment grounding conductors, and bonding jumpers. The NEC also specifies the requirements for grounding electrodes such as ground rods and ground plates. In summary, a single-point ground is a crucial concept in electrical grounding, referring to the practice of connecting all grounding conductors to a single, central point. The purpose of a single-point ground is to minimize ground loops and voltage differences, which can cause electrical noise and create a shock hazard. By using a single-point ground and by following the requirements of the National Electrical Code, it is possible to create a safe and effective grounding system. Bonding jumpers are essential components of a grounding system, used to connect metallic parts together to ensure electrical continuity and equalize potential. This practice, known as bonding, minimizes voltage differences between conductive surfaces, reducing the risk of electric shock. Bonding jumpers are typically used to connect metal water pipes, gas pipes, metal conduits, and other metallic objects to the grounding system. By connecting these objects together, they are all brought to the same electrical potential, preventing voltage differences that could create a shock hazard. The National Electrical Code, or NEC, provides specific requirements for bonding jumpers. The NEC specifies the size and type of bonding jumpers that are required for different applications. The NEC also specifies the methods for connecting bonding jumpers to metallic objects. Bonding jumpers must be sized according to the size of the circuit conductors that supply the equipment. The larger the circuit conductors, the larger the bonding jumpers that are required. This ensures that the bonding jumpers are able to carry the maximum fault current without overheating or melting. Bonding jumpers must be made of copper or other corrosion-resistant material. This prevents the bonding jumpers from corroding over time, which could reduce their effectiveness. Bonding jumpers must be connected to metallic objects using listed connectors. Listed connectors are designed to provide a reliable electrical connection between the bonding jumper and the metallic object. The connectors must be installed according to the manufacturer's instructions. In addition to bonding metallic objects, bonding jumpers are also used to bond equipment together. This is known as equipment bonding. Equipment bonding is required for all electrical equipment that is likely to become energized, such as motors, transformers, and switchgear. Equipment bonding ensures that the equipment is properly grounded and that any fault current will be safely conducted back to the source. The NEC specifies the requirements for equipment bonding. The NEC requires that all equipment be bonded to the grounding system using equipment grounding conductors. Equipment grounding conductors are typically made of copper and are run with the circuit conductors. The equipment grounding conductors are connected to the equipment enclosure and to the grounding busbar in the electrical panel. In summary, bonding jumpers are essential components of a grounding system used to connect metallic parts together to ensure electrical continuity and equalize potential. The NEC provides specific requirements for bonding jumpers, including the size, type, and installation methods. By following the requirements of the NEC, it is possible to create a safe and effective grounding system that protects people from electric shock. The grounding electrode conductor, or GEC, is a critical component of an electrical grounding system, providing the connection between the grounding electrode and the grounded conductor, typically the neutral, at the service equipment. Its primary function is to create a lower impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses during a ground fault. The grounding electrode conductor connects to the grounding electrode, which can be a ground rod, ground plate, or metal water pipe that is buried in the earth. The grounding electrode provides a direct connection to the earth, which serves as a reference point for the electrical system. The grounding electrode conductor also connects to the grounded conductor at the service equipment. This connection is typically made at the main grounding busbar in the electrical panel. The main grounding busbar is the central point for all grounding connections in the electrical system. The National Electrical Code, or NEC, provides specific requirements for the grounding electrode conductor. The NEC specifies the size and type of grounding electrode conductor that is required for different applications. The NEC also specifies the methods for connecting the grounding electrode conductor to the grounding electrode and the grounded conductor. The size of the grounding electrode conductor is based on the size of the service entrance conductors. The larger the service entrance conductors, the larger the grounding electrode conductor that is required. This ensures that the grounding electrode conductor is able to carry the maximum fault current without overheating or melting. The grounding electrode conductor must be made of copper or other corrosion-resistant material. This prevents the grounding electrode conductor from corroding over time, which could reduce its effectiveness. The grounding electrode conductor must be connected to the grounding electrode and the grounded conductor using listed connectors. Listed connectors are designed to provide a reliable electrical connection between the grounding electrode conductor and the grounding electrode and grounded conductor. The connectors must be installed according to the manufacturer's instructions. In addition to the NEC requirements, there may also be local codes and regulations that apply to grounding electrode conductors. It is important to check with the local authorities to ensure that the grounding electrode conductor is installed in accordance with all applicable codes and regulations. A properly installed grounding electrode conductor is essential for the safety of the electrical system. It provides a low impedance path for fault current to return to the source, which helps to quickly trip the overcurrent protective device and clear the fault. This helps to prevent electric shock and fire. In summary, the grounding electrode conductor is a critical component of an electrical grounding system, providing the connection between the grounding electrode and the grounded conductor at the service equipment. The NEC provides specific requirements for the grounding electrode conductor, including the size, type, and installation methods. By following the requirements of the NEC and local codes, it is possible to create a safe and effective grounding system that protects people from electric shock and fire. The National Electrical Code, frequently abbreviated as NEC, is a widely adopted standard in the United States for the safe installation of electrical wiring and equipment. While it is not itself a law, it is often adopted by state and local jurisdictions, becoming legally enforceable. The NEC is published by the National Fire Protection Association, or NFPA, and is updated every 3 years to reflect changes in technology and best practices. The NEC covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It provides detailed requirements for the safe installation of electrical systems in residential, commercial, and industrial buildings. The NEC is organized into chapters, articles, and sections. Each chapter covers a specific area of electrical installation, such as wiring methods or grounding. Each article covers a specific topic within the chapter, such as conduit or ground rods. Each section provides detailed requirements for the specific topic. The NEC is a complex document and it can be difficult to understand and apply. However, it is essential for electricians and other electrical professionals to be familiar with the NEC in order to ensure the safe installation of electrical systems. The NEC is not a design manual. It does not tell electricians how to design an electrical system. Instead, it provides minimum requirements for the safe installation of electrical systems that have already been designed. The NEC is a living document, and it is constantly being updated to reflect changes in technology and best practices. It is important for electricians and other electrical professionals to stay up to date on the latest changes to the NEC in order to ensure that they are installing an electrical system safely. The NEC is not the only electrical code that is used in the United States. Some states and local jurisdictions have their own electrical codes that are based on the NEC. It is important to check with the local authorities to determine which electrical codes apply in a particular area. The NEC is an important tool for ensuring the safe installation of electrical systems. By following the requirements of the NEC, electricians and other electrical professionals can help to prevent electric shock, fire, and other electrical hazards. In summary, the National Electrical Code is a widely adopted standard in the United States for the safe installation of electrical wiring and equipment. The NEC covers a wide range of electrical topics and provides detailed requirements for the safe installation of electrical systems in residential, commercial, and industrial buildings. It is essential for electricians and other electrical professionals to be familiar with the NEC in order to ensure the safe installation of electrical systems. Overcurrent protection is a critical aspect of electrical safety, designed to protect electrical circuits and equipment from damage caused by excessive current flow. Overcurrent can result from various scenarios, including short circuits, overloads, and ground faults. Without proper overcurrent protection, these conditions can lead to overheating, insulation breakdown, equipment failure, and even fire. The most common overcurrent protective devices are circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when it exceeds a predetermined level. They can be reset and reused after the fault is cleared. Fuses, on the other hand, are single-use devices that contain a fusible link that melts and breaks the circuit when the current exceeds a specified value. Fuses must be replaced after they have blown. The selection of the appropriate overcurrent protective device depends on several factors, including the ampacity of the circuit conductors, the type of equipment being protected, and the expected fault current levels. The National Electrical Code, or NEC, provides detailed requirements for overcurrent protection, including the sizing of circuit breakers and fuses. The NEC requires that overcurrent protective devices be sized to protect the circuit conductors from overheating. The ampacity of the circuit conductors must be equal to or greater than the rating of the overcurrent protective device. The NEC also provides requirements for the location of overcurrent protective devices. Overcurrent protective devices must be readily accessible and must be located at the point where the circuit originates. This ensures that the entire circuit is protected from overcurrent. In addition to circuit breakers and fuses, other types of overcurrent protective devices are available, such as motor overload relays and ground fault circuit interrupters, or GFCIs. Motor overload relays are designed to protect motors from overheating due to overloads. GFCIs are designed to protect people from electric shock by detecting ground faults. Overcurrent protection is an essential part of electrical safety. By providing a means to automatically interrupt the flow of current during overcurrent conditions, overcurrent protective devices help to prevent damage to electrical circuits and equipment, and protect people from electric shock and fire. Regular inspection and testing of overcurrent protective devices are important to ensure that they are functioning properly. Circuit breakers should be tested periodically to ensure that they trip at the correct current level. Fuses should be inspected to ensure that they are not damaged or corroded. In summary, overcurrent protection is a critical aspect of electrical safety, designed to protect electrical circuits and equipment from damage caused by excessive current flow. Circuit breakers and fuses are the most common overcurrent protective devices. The selection of the appropriate overcurrent protective device depends on several factors, including the ampacity of the circuit conductors, the type of equipment being protected, and the expected fault current levels. The NEC provides detailed requirements for overcurrent protection.